Okay, in this next video we're going to look at one final example for the beta distribution, which is the example that A is equal to 2 and B is also equal to 2. So P is beta distributed to 2. Okay, so that means that the probability density function on the open interval 0, 1 is going to be some normalizing constant times x to the power of a minus 1, which in this case is 2 minus 1, times 1 minus x to the power of b minus 1, which is also 2 minus 1. So we get that this is c times x times 1 minus x, basically. Okay, so now all we need to do is firstly try and plot this, and secondly try and work out a normalizing constant for this. So this is a quadratic equation, and if we expand it out, we're going to get cx minus cx squared. So we're going to get a negative quadratic equation, which means that it's going to look like a non-smiley face, an unhappy smile, basically, providing, of course, that c is a positive value. If c is a negative value, then of course it's going to look like a smiley face, but we're going to see that it is in fact a non-smiley face, an unhappy face. And we also know where its zeros are. We know that it has a 0 at the point x is equal to 0. So if I draw this, it goes through the x-axis there at x is equal to 0, and it also goes through the x-axis at 1. And we also know that we want it to be positive on the interval 0, 1, because we want its integral on 0, 1 to equal 1. So that really tells us what this is going to look like. It's going to look something like that, basically. Because there are only really a few possibilities. It either looks like that. We don't, of course, know how stretched it is. It could be more stretched like this. Depending on what this constant is. We will find it by stating that we want the area to be equal to 1, but what we know is that it's not a happy face like those two. So it is not one of these two here, because they have negative values on the interval 0, 1. So we know it is an unhappy face like this one here, basically. So it's going to look something like that. So let me highlight that green. The green one is the one we think it does look like, and we just don't know how stretched it is. Okay, right. So now that we've got a good idea of, of course, that is not what the probability density function looks like. That is what this function looks like on the whole interval. The probability density function, of course, is only this bit of it. So it looks like that, and then of course it goes on and looks, it goes on like that on the from 0 onwards and from 1 onwards. It's 0 everywhere else. Okay, so let's try and work out the normalizing constant. So we want the integral of cx minus cx squared dx between 0 and 1 to equal 1. Okay, so let's pull out that normalizing constant, and we get that the integral between 0 and 1 of x minus x squared dx needs to equal 1. So let's work out what this integral between 0 and 1 of x minus x squared is. The integral between 0 and 1 of x minus x squared dx. So this is a very basic calculus problem now. So the antiderivative of x is x squared over 2. The antiderivative of x squared is minus x cubed over 3. So we evaluate that between 0 and 1, basically. So firstly evaluate this at 1, and we get a half minus a third, and then we subtract off what it is evaluated at 0, basically. So if we evaluate this at 0, we'll get 0 squared over 2 minus 0 cubed over 3, which is of course just 0. So those bits go to 0, basically, and then what we do is so that bit doesn't count, so we now just need to calculate what is a half minus a third, which is just a sixth, and therefore this integral is a sixth. So what we now know is that c times a sixth, so c divided by 6, needs to equal 1, and we therefore get that c needs to equal 6. So this probability density function now is going to be equal to 6x 1 minus x. And that concludes our introduction to the beta distribution. In the next video, what I will do is show you a method for calculating this normalizing constant in a much more general setting. So we're going to calculate it in the general case that a and b are integers, so a and b are going to be integers, and a and b are also going to be greater than or equal to 1, which is basically the case that the exponents here, these things up here, are going to be positive, well, not negative integers.